Welcome back to the series of lectures on high-performance scientific computing. In this video, we will review the concepts of using CUDA for programming GPUs. First of all, what is CUDA? CUDA is Compute Unified Device Architecture, which is a parallel computing platform by NVIDIA, and this is specific to the NVIDIA General Programming Graphic Processing Units. It provides a lower level of programming model for the GPUs, and it allows for massive parallelism using hundreds of thousands of threads or other thousands of threads. It is supported in the C, C++, and Fortran. It is used for high-performance computing for artificial intelligence, machine learning, simulations, and a lot more. First of all, why do we want to use CUDA? Because if you use CUDA, we have direct control of the graphic processing unit resources or GPU resources. It gives us much higher performance when you compare it to directive-based programming like OpenMP and OpenACC. Because we are doing programming at a much lower level, the programmer has a lot more control and is able to extract way more performance. So this is very essential for doing deep learning algorithms, scientific computing, and also gaming. It provides extremely fine-grained parallelization. So what is effectively the CUDA execution model? So we have to understand that there are two concepts over here. You have the host, which is the CPU, which is a normal CPU processor, compute processor, and you have a specialized device called a GPU, which is the graphics processing unit. So the host essentially manages the execution and the main memory. The device essentially executes parallel kernels or parts of the program which can be effectively parallelized. You have an idea of a grid, block, and a thread hierarchy. So if you look at the graphics processing unit, typically it has several streaming multiprocessors, and each multiprocessor has several parallel cores. These are lightweight cores which are able to execute very simple operations, and they work in what is called as the SIMD mode, or single instruction multiple data. For example, if you want to add multiple data members of an array, AI is equal to BI plus CI. In the CUDA execution mode or in the GPGPU execution mode, several of the members, BI plus CI, will be added together in one shot and will be stored in their respective AIs. So this device executes such kernels in parallel. But obviously, you will have a very long array, which can be then sort of subdivided into blocks. So each block will contain singular threads which will work on a single data item, and then the blocks can further be organized into grids. So grids will essentially contain multiple blocks, and blocks will contain multiple single threads. So to enable CUDA, first of all, you need a CUDA capable device, which is typically a graphics processing unit sold by NVIDIA. You need to install the NVIDIA CUDA toolkit, which allows you to program, and then you have to use the NVCC compiler. You need to invoke the NVCC compiler using the NVCC command for the program that you have written, program.cu. This program will now contain different bits of codes. It will contain bits of codes which will run on the CPU, for which the NVCC compiler will call the underlying system C or C++ compiler and compile that relevant bits of code. For bits of code which are annotated and marked to run on the GPU device, the NVCC compiler will then generate instructions which will then execute on the NVIDIA GPU. So obviously you need a system with an NVIDIA GPU. So typically the programming model contains this. So you have a kernel function, that's the bit of code that actually runs on the GPU, which is massively parallel. You then have to have a launch configuration which specifies the grid and the block dimensions. You also have to understand that there is a certain memory hierarchy, that you have a global memory, you have the shared memory between the device, you have the local memory, and then finally registers. You have synchronization. Different threads again will run at different speeds. So you need to synchronize different bits of threads using the sync threads function. Remember, we're doing all this on a parallel device, and different threads could run at different speeds because they might be working slightly harder or slightly less harder based on the algorithm that is there. So if you look at the basics, so you will see that a function which is annotated with the identifier underscore underscore global underscore underscore essentially tells the compiler that that function needs to run on the GPU. That means that bit of code, in this case the function add, is going to be compiled with instructions which are capable to be run on the GPU. You then are basically going to figure out what is the particular index using the block ID and the thread ID. Each thread will process one element, and several threads in one block are usually executed in one shot using the SIMD approach. So in this case, we have to launch the CUDA kernel by invoking the function add. You have to supply it with information of the grid size and the block size using the chevron symbol, which is the 3 greater than and the 3 less than symbols. You also need to have the device copies of the specific variables where you need to work. So in this case, we are specifying the execution configuration, saying that each block size is 256, and we are calculating the grid size based on the size of the data. Getting the optimal grid size and the block size mapping is key for the performance. We also need to understand what the CUDA memory hierarchy is. The global memory is large, which is slow, and is used for transferring data between the host and the GPU. Shared memory is used within a block of threads. It's extremely fast. You can think of it similar to as a CPU cache. And then finally, you have registers at the SMP level, which is very fast but very limited. And then you can optimize the texture and constant memory. So having an understanding of how this memory is very similar to the memory hierarchy of CPUs. As far as possible, we should keep data as close to yourself as possible. Hopefully the data, most of it lies in shared memory, and you do fewer fetches from the global memory and even fewer fetches between the host and the device. Because you're programming on a separate physical device, you have to physically do memory management. You need to allocate and deallocate memory using the CUDA malloc function. Deallocation is done using the CUDA free function, and you need to explicitly copy data using the CUDA memcopy function, which is bidirectional. You can do CUDA memcopy from host to device, and the same function can be used to do CUDA memcopy from device to host. You can do tricks like pinned memory for faster host GPU transfers. And if we have unified memory, this simplifies memory management. Thread synchronization. Because each of these threads are now being running in blocks, and each of these blocks are then sort of being executed on the symmetric multiprocessors, they will run at slightly different speeds. Also, each thread, it's quite possible that your algorithm is executing slightly different parts of the program. So there could be some asynchronicity which develops within the threads. And for that, we need to use sync threads to ensure that all the threads are at the same point before you go to further parts of the program. Similarly, we need to have reduction operations and we need to have atomic operations. Multiple threads might need to access the same variable. And in this case, we are showing the atomic add function. So several threads are inserting their value into this variable sum. And because we need to have data coherence, it is important to use this atomically, i.e. essentially only one thread will be able to access the variable sum at any given point of time so that the data is not corrupted. We also need to calculate the occupancy, which is basically optimizing the thread and block usage to see if all the memory and all the symmetric multiprocessors are being efficiently used. We again looked at the case study of the matrix multiplication, where we wrote a device kernel to do the matrix multiply, and we did this using different blocks and different threads. And in this case, we used a two-dimensional thread grid for the parallelism. We had optimized the shared memory for better performance. Similarly, CUDA is very efficient in doing image processing, doing filters like edge detection, blurring, and it can do extremely good shared memory optimization for convolution filters. It has been successfully used for CFD problems for solving Navier-Stokes equations, especially for grid-based parallelism and fluid simulations, where we looked at finite difference type of methods. We had looked at the solution of the Laplace equation using the successive over-relaxation technique on a GPU. And we can also do Monte Carlo simulations using parallel random number generation, and we had looked at how we could integrate a function numerically using Monte Carlo simulations. We had studied different debugging tools like CUDA GDB. Profiling is very important. Remember, for the vast majority of time, CUDA programs spend their time transferring data between the host and the device. So the profiler actually allows us to see where the program is spending most of its time, whether it's on the device to host transfer, host to device transfer, or on actual computes, and which of these functions are taking most of this time. So profiling tools like NVProf and the NVIDIA Insight systems give you this idea for optimizing the code further. So just to compare the CUDA versus OpenMP versus OpenACC models. So CUDA is a little bit more explicit in the sense where you have explicit control in allocating memory, writing what functions are going to go onto the device, and writing explicit device code. Whereas OpenMP and OpenACC are directive based. CUDA works only with NVIDIA GPUs. OpenMP and OpenACC work with more sort of general heterogeneous machines, so they have medium to high portability. CUDA is a little bit more complex to use because you have to write a lot more code, whereas OpenMP and OpenACC are very easy. Since you're just adding directives, you could take a serial code and quickly parallelize it. Finally, the performance control. CUDA, because you're writing a lot of low-level code, you have extremely high control over the performance. You can write extremely efficient code with CUDA. With OpenMP and OpenACC, the performance gain is sort of medium because you're not having that much explicit control over what is going on to the device and further optimization on the devices. So if you have a code and if you want to put in more effort and extract the maximum possible efficiency, and you're very sure that you're going to run only on NVIDIA hardware, then it is probably better to go with CUDA. To summarize, CUDA enables very fine-grained GPU parallelism. It requires explicit memory and thread management. It is effectively used in artificial intelligence, machine learning, HPC, and other scientific computing. It is extremely optimized for memory usage and parallelism to improve the performance. Thank you.